Welcome to Maths with EJD. In this video, I'll be talking about the De Moivre's theorem under complex numbers. It is such an important concept in relating with complex numbers. The outline, we'll be looking at the introduction, the statement of the De Moivre's theorem, some applications of the theorem, then we'll reach a conclusion, and then we'll have some practice questions to try our hands on. Of course, in the introduction, our objective is to understand the Moivre's theorem and its applications in complex number theory. So straight to the point, the statement of the De Moivre's theorem is pretty easy. It is the idea that for any integer n and any complex number z, which is r cos theta plus I sin theta, where r is the modulus and theta is the argument or the angle, the Moivre's theorem states this, that if r into cos theta plus I sin theta is raised to power n, then you can now express that as r raised to power n and then cos n times theta. So you see the r is carrying the power, but then the angles are multiplied by the power to which the expression is raised. Now, this actually has a proof, which you can, do binomial expansion on this Euler's formula, and then you get all that. But I mean, this is, for now, let it suffice to say this is the statement, and you can use this as simple as it seems, right? It has far-reaching implications in solving problems, as you're going to see going forward. So let's look at some applications of De Moivre's theorem. First, you can use De Moivre's theorem to find powers of complex numbers. You can use it to simplify trigonometric expressions. With it, you can find the roots of complex numbers and also solve certain differential equations. But in this video, our focus will be on these first three as we proceed. Okay. All right. So we go to the next slide with the first example. So how do you find powers of complex numbers? Here, the Moivre's theorem allows us to find powers of complex numbers efficiently. The word efficient is the deal, efficiently. So for instance, consider raising the complex number z equals 1 plus I to power 5. So it's like you have 1 plus I raised to power 5. Of course, we can do this using binomial expansion, but the deal is that it will not be efficient. Maybe 5 is even easy to handle. What if the power is like 15? That'll be a lot of trouble, a lot of stress right there. So, but with De Moivre's theorem, we can actually do that so efficiently, okay? And De Moivre's theorem, as you can see already, operates in polar form. So that's why it's important whenever you have a function like this, you want to first express it in polar form so that you can easily use the Moivre's theorem on it. So, in polar form, you need the modulus, which is square root of a squared plus b squared. From this z now, we can see that a is 1, that's the real part, and b is also 1, the imaginary part, the coefficient of I. The I is the imaginary unit, like we've been saying. So you have a equals 1 and b is also equal to 1. Okay, so r now is equal to square root of a squared plus b squared, and that is square root of 1 squared plus 1 squared. That is square root of 2, like that. And then to get the argument or the angle, so you have to say arctan of b over a. That's b divided by a, and that is for pi over 4. Pi over 4 is 45 degrees. Normally tan 45 degrees is equal to 1. So it means that 45 degrees is equal to arctan of 1. And you know that 45 is the same thing as pi over 4 because pi itself is 180 degrees, like that. Okay, so once you get all this, once you get your r and your theta, it means that you can now say z is equal to r, which is root 2 now, cos theta pi over 4 plus I sine theta, which is pi over 4. But then our goal is to obtain z raised to power 5, which is 1 plus I raised to power 5. Now we have 1 plus I raised to power 5. We have 1 plus I to be this, to be this whole expression. Now we have to go raise it to power 5, And that's the next thing we are concerned with. Okay, so let's see this. So using the De Moivre's theorem now, you have z raised to power 5 equals all this expression raised to power 5. And as expected, you have r raised to power n. So that's root 2 raised to power 5. And then cos 5 pi over 4 plus I sine cos pi over 4 plus I sine pi over 4 all raised to power 5. And from the Moivre's theorem, this root 2 will be raised to power 5, and then the angles will be multiplied by 5. So pi over 4 times 5, pi over 4 times 5. Okay, so that's what but root 2 raised to power 5 means you have root 2 times root 2, 2, 3, 4, and 5 like this. So root 2 times root 2 is 2. Root 2 times root 2 is also 2. And this is root 2. So 2 times 2 is 4. 4 times root 2. That's why root 2 raised to power 5 is 4 root 2. And then the angles are cos 5 pi over 4 sine 5 pi over 4. Now, how do you unpack this particular 5 pi over 4? Now, pi is 180. So it's like 5 times 180 divided by 4. So 4 here is 1. 4 here is 45. 5 times 45 is 225 degrees. So how do you take care of 225 degrees? You need to understand the idea of 4 quadrants, that, this here, all is positive. That's from 0 degrees to 90 degrees. Everything, whether sine, cosine, or tangent, is positive. And here, between 90 and 180 degrees, only sine is positive. Tan and cos are negative. And here you have 270 degrees. Between 180 and 270 degrees, only tan is positive. Then sine and cos here are negative. And lastly, between 270 degrees and 360 degrees, only cosine is positive. Tan and sine are negative between 270 and 0 degrees. And now we are dealing with 225 degrees. 225 degrees naturally falls into this place. 225 degrees, you find 225 degrees right here. It's here. Okay, so it means that since you are dealing with cos and sine, they are automatically going to be negative. That's why you see these negative values right here. Okay, and what does it correspond with? To know what it corresponds with, you have to say, you have to say 225 minus 180. 225 minus 180, and that is simply 45 degrees. So 225 in the third quadrant coincides with 45 degrees in the first quadrant. But because it is sine and cos are negative in the third quadrant, so you have minus minus. And what is sine 45 degrees in the first quadrant is actually 1 over root 2. Okay? And that is 1 times root 2 divided by, so that's root 2 times root 2. That's rationalizing. So you have root 2 all over. Root 2 times root 2 is 2. So that's why third quadrant minus, 225 is in third quadrant, right? That's why it's negative for cosine, it's negative for sine. But then because it corresponds to 45 degrees, then 45 degrees, cos of 45 and sine of 45, they are the same. And they are 1 over root 2. And if you rationalize, you get root 2 over 2. That's why you have minus root 2 over 2 minus I root 2 over 2. Like that. So it's important to understand that concept, how to break down angles that way. Okay. Now that is sorted, so we need to simplify all this, what we have left. We need to simplify what we have left. So we have 2 cancel, 2 in 4 is 2. Root 2 times root 2 is 4. Is 2, Root 2 times root 2 is 2. 2 times 2, 4. This minus is what you have here. Then this minus is here again. Same, 2 cancels 4, that's 2. Then root 2 times root 2 is 2. That 2 times 2, 4. So it means that 1 plus I raised to power 5 is the same thing as minus 4 minus 4I. Now, if you did the normal binomial expansion thing, you still get the same thing, right? But that's probably that's a more difficult way to go. Or even if it is not difficult for 5, what if we say power 15? That's going to be a lot. So that's why the Moivre's theorem is very useful in this kind of situation. Okay. All right. So that's that. How about simplifying trigonometric expressions? The Moivre's theorem helps in simplifying trigonometric expressions involving powers of trigonometric functions. For example, consider simplifying cos theta plus I sine theta raised to power 7. Consider simplifying this. Of course, the Moivre theorem already told us that cos theta plus I sine theta raised to power 7 should simply be cos 7 theta plus I sine 7 theta. And if you don't want to go that way, you can use the Euler's formula, which is cos theta plus I sine theta, which is the same thing as e raised to power I raised to power I e raised to power I theta. And if you raise that to power 7 using indices, you get e raised to power I 7 theta. And this is the same thing as this expression. So it's really helpful to get rid of, to quickly do stuff with trigonometric expressions. So this simplification is particularly useful when dealing with trigonometric identities and equations involving complex numbers. Okay? Now, let's see another form of simplification of trigonometric expressions. So we want to express cos theta and cos 3 theta and sine 3 theta in terms of cos theta and sine theta, respectively. That means for cos theta, express it totally as in terms of cos theta, and sine theta, 3 theta, express it as in terms of sine theta alone, using the Moivre's theorem and binomial expansion. That's what we want to do. So, if we already know that cos theta plus I sine theta raised to power 3 is the same thing as cos 3 theta plus I sine 3 theta. So it means we can also come back and say cos 3 theta plus I sine 3 theta is the same thing as cos theta plus I sine theta raised to power 3, And from here now we can use binomial expansion. And here the idea is this. You have a plus b raised to power 3. For power 3, we can still use what we call the Pascal's triangle, where if it is raised to power 0, the coefficient is 1. If it is raised to power 1, the coefficient is 1. That's, if imagine a plus b raised to power 0, anything raised to power 0 is 1. Then raised to power 1, that would be a, b, that's 1a plus 1b. So if it is raised to power 2, you have 1, 2, 1. That's 1, 1 plus 1, 2, then 1. So that means that's where you have a squared plus 2ab plus b. And then finally you have for power 3, you have 1 plus 2 3, 2 plus 1 3, then 1. So the coefficient of something in power 3 is 1 3 3 1. That's why you have 1a raised to power 3 plus 3a raised to power 2b plus 3a b raised to power 2 plus b raised to power 3. So 1 3 3 1, like that. And then you see the first one carries power 3, and it's a cubed, a squared, a, and a0. And here b0 starts, then b1, b2, b3. So it goes like that. So that's exactly what we are going to do for this cos theta plus I sine theta raised to power 3, where cos theta can be seen as a and I sine theta can be seen as b. Okay, so now that that is taken care of, we can now say that so this is like a, so cos theta raised to power 3, that's cos cube theta. Then next you have coefficient 3, then cos theta raised to power 2, that's cos square theta. Then I sine theta raised to power 1. Then next you have coefficient 3 again. Cos theta will reduce in power again, that's cos theta into I sine theta raised to power 2, plus finally I sine theta raised to power 3. So that's the deal for that. So the next thing, you have cos cube theta plus, just rearrange. So I have I3 sine theta cos square theta, like this. Then here, now you see I squared is equal to -1, like we've always known, because it is root 1 times root 1. Root -1 times root -1, that's -1. So I squared is -1. So that's the minus you have here. And then sine theta squared is sine squared theta. So we have 3 sine squared theta cos theta, like this. And then lastly, I cube, I raised to power 3 for here, I raised to power 3. So you have I raised to power 3 is the same thing as I squared times I. So I squared is minus already, -1, then I. So it means that I cube is minus I. That's what you have here. And this is sine theta raised to power 3, sine cube theta. Okay. So that is settled again. And then we go on and tidy things up further. So at this point, you can see that this cos cube theta and -3 sine square theta cos theta do not have I, whereas I sine square theta cos square theta and -I sine cube theta both have I. So we can put them together like that. Okay, so let's now collect the ones without I together. So we have cos cube theta minus 3 sin square theta cos theta. And then for the ones with I, we have 3 sin theta cos square theta minus sin cube theta. Again, that is settled. So at this point, you could just say cos 3 theta, cos 3 theta is equal to all this, and sin 3 theta is equal to all this. But we are expected to express cos 3 theta totally in terms of cos theta and sin 3 theta totally in terms of sin theta. So in that case, our job is not finished. So since one is for cos, any sign we see, we have to change it to cos. So we know sin square theta, can be changed following this, that sin square theta plus cos squared theta is equal to 1. That means that sin squared theta is equal to 1 minus cos squared theta. And in the same way, cos squared theta is equal to 1 minus sin squared theta. Very important. So you have cos cube theta minus 3. Sin squared theta now is 1 minus cos squared theta times this cos theta plus I. You have 3 sin theta. Cos squared theta now, since this one is about sin theta, so cos squared theta is 1 minus sin squared theta minus sin cube theta. So we now tidy all this up. So we have cos cube theta is here. So minus 3 times 1, minus 3 times cos theta, that's minus 3 cos theta. Minus times minus is plus. 3 times cos squared theta, that's 3 cos squared theta times cos theta, that's 3 cos cube theta, settled like that. So you have your I out here. So 3 sin theta times 1, you have 3 sin theta. 3 sin theta times minus 3 minus sin squared theta, that's minus 3 sin cube theta. And then you have this minus sin cube theta right here. So the next thing is just to tidy things up, collect things that look alike together. So you have now you have cos cube theta plus 3 cos cube theta. That's 4 cos cube theta minus 3 cos theta here. Then I. So you have 3 sin theta minus 3 sin cube theta minus sin cube theta. That's minus 4 sin cube theta. So at this point now, you can now conclude, it's all done. So you can see already that cos cube theta is the same as this because it has no I. And then you can also see that I sine cube theta is the same as this because they both have I. Okay. And if that is the case, okay, let me do that better. So this I sine cube sine 3 theta, right? So it means that cos 3 theta is equal to 4 cos cube theta minus 3 cos theta, and then you have sine 3 theta equals 3 sine theta minus 4 sine cube theta. So you can use the Moivre's theorem to simplify trigonometric expressions. Okay, so let's talk about finding the roots of complex numbers. Finding the roots of complex numbers. So here, you want to find the nth root of a complex number. You can easily find the root of real numbers. Square root of 8 is simply 2, and you move on with your life. I mean, it's 2 roots 2, sorry. Cube root of 8, cube root of 8 is 2, and that is it. So, like that. But here, we are dealing with complex numbers, so we need the Moivre's theorem comes in pretty handy right here. And to find the nth root of a complex number, z equals r cos theta plus I sin theta. This is what you use. You use the nth root of z, as z raised by 1 over n, is the nth root of r cos theta plus theta over n plus 2k pi over n plus I sin theta over n plus 2k pi over n. Now, k is defined as 0, 1, 2, up to a step short of the root you're looking for. So if you're looking for the fourth root, your k would be 0, 1, 2, 3. If you're looking for the third root, I mean, if n is 3, power 3, then k would be 0, 1, 2. So, and that will give you the results you need, because third root means you're looking for 3 things, fourth root means you're looking for 4 things, but then you start from 0. Okay, so we go further into this. Yeah, so the question we have to deal with here is to take care of the cube roots of z equals minus 8. Cube root of z equals minus 8. It's something like you have z plus cube root. So you have z cube plus 8 equals 0. That it's more like you're solving this kind of problem. That's what the idea of that is. Okay. So to find the cube root of the complex number z equals minus 8, we start by expressing z in polar form. Since z is -8, lies on the negative real axis, okay? So it's like you have something like this. You have -8 somewhere around here. So it lies on the negative real axis. So its polar form will have a modulus of 8. So we are going to, so our r is going to be 8. And, since this is negative, right? So it means the argument also, the argument theta now is going to be pi. And the reason for that is this, you know, so if you have cos pi is -1, and sin pi is 0. So that if you have 8 times -1, you have -8, and this is I sine. So, I mean, this is just 0, right? So this is exactly the same thing as -8. Very important. And now that that is taken care of, and we are interested in the cube, right? We are interested in the cube. That's the third root, the cube root. That's so the n is 3 here. So, of course, it means we have z raised power I raised power z raised power 1/3, and that is 8 raised power 1/3. And then the angles now will be pi/3 plus 2k pi/3 plus I sine pi/3 plus 2k pi/3. Now, for the k now, since n is 3, it means that our k will have to be 0, 1, and 2. 0, 1, and 2. So, since it is 0, 1, and 2 now, so don't forget, we have to keep referring to this. So when k is 0, when k is 0, it means we have just pi/3. So because this will be 0 and this will be 0, gone. So we have pi/3. And that is what dictates, what we have here, pi/3 each. And then for the next one, when k is 1, k is 1, so we have pi/3 plus 2 times 1, 2, plus pi. That is 2 pi over 3. So when you put this together, that's 3 pi over 3. And that's what we have next. So that's why we have z2, which is cos 3 pi over 3 plus I sine 3 pi over 3. And lastly, when k is 2, right, you have pi over 3 plus 2 times 2, 4. That's 4 pi over 3. Totally, that will be 5 pi over 3. Okay? And that's why we have Z3 to be now 8 raised by 1/3 cos 5 pi over 3 plus I sine 5 pi over 3, like this. Okay. So now we try to simplify all this. Now pi over 3 is pi, pi is 180 degrees, right? Pi over 3 is 180 over 3, that's 60 degrees. And we know cos 60 degrees is popular. Cos 60 degrees is 1/2. And sine 60 degrees is √3 over 2. Okay. So, and 8 raised power 1/3 is simply 2. So if you expand this now, 2 times half is 1, plus I, 2 cancels 2 again, you have √3. So that's why Z1 is 1 plus I √3. Now for the second one, pi cancels pi, 3 cancels 3. I mean, 3 cancels 3, sorry. So you have cos pi plus sine pi. Now, cos pi is -1. Sine pi is 0. That was the kind of thing we started with. So, and this is 2, right? So 2 times -1, -2. The other part is 0, so we don't bother about that. And lastly here, we have 5 pi over 3. 5 pi over 3 means you have 5 times 180 divided by 3. 3 here is 1, 3 here is 60. 5 times 60 is 300 degrees. I think I just did something about the 4 quadrant, right? 300 degrees. So 300 degrees is between 270 degrees and 360 degrees. And in this quadrant, only cosine is positive. Only cosine is positive because 300 degrees is here. And then so this 300 degrees corresponds with 360 minus 300, that is 60 degrees in the first quadrant, okay? And only cosine is positive. So it means that if you're looking for the cosine of 300 degrees, it is a positive value, all right? So it is positive, and the cosine of, and it corresponds to 60. So cosine of 60 is 1/2 again, because that was the kind of thing we did here before, 1/2. So it's 1/2 again. And then for sine 300 degrees, in the fourth quadrant, 300 degrees is, the sine of 300 degrees is negative. So we have minus, now sine 60 is again √3/2. So, and of course, this is going to be 2. 2 times half is 1. Then this minus is what you have here. Then 2 times root 3 over 2, 2 cancels 2, and you have I root 3. Okay, so these are the three. So at the end of the day now, you have these three roots. So the first root is 1 plus I root 3. The second one is minus 2. The third one is 1 minus I root 3. And that's why we have all this here. So the cube root of z equals minus 8 as z equals 1 plus I root 3. Z2 is minus 2 and Z3 is 1 minus I root 3. Okay, so interestingly, it has a geographical, it has a graphical representation. So these roots represent the vertices of an equilateral triangle. So you can see this triangle is all sides are equal, So the roots represent the vertices of an equilateral triangle in the complex plane. So in the complex plane now, the equilateral triangle is centered at the origin 0, 0, right? So those three roots that we have, the first root we had was 1 plus 1.73, root 3, right, is 1.732. So 1 real, 1.732 complex, that's root 3. And then the second one is minus 2, as you can see here. And the third one is 1 minus 1.732 again. So the roots represent the vertices of an equilateral triangle in the complex plane centered at the origin and enclosing the point minus 8. Enclosing the point minus 8. Okay, so we have all that, and we can come to the conclusion now that, in summary, the Moivre's theorem is a powerful tool in handling powers and roots of complex numbers, and it finds applications in various mathematical problems. So understanding the De Moivre's theorem actually helps you to solve a lot of problems that would naturally look difficult. So understanding and applying the De Moivre's theorem simplifies complex number computations and facilitates problem solving in mathematics. Okay, so we are done with that. So I like you to see some questions you can try your hands on. Um, okay, so we have this here. Oh, okay. There are still some questions ahead. Yeah, sorry. Yeah, very important. Good. So we have practice questions 1. Use the Moivre's theorem to find 1 plus I raised power 10. Now imagine you trying to use binomial expansion for this. That would be a lot of stress, as you can already imagine. So 1 plus I raised to power 10, 3 minus 4I raised to power 6, minus 2 plus 2I raised to power 5. Then find all the cube roots of 8I. What we did before was for 8, for minus 8. So now you're dealing with 8I, then minus 27. So that's close to minus 8. And you have 64 cos pi over 3 plus I sin pi over 3. Then, just all you need to do is apply the rule. Then solve this equation. Z raised to power 4 equals minus 16. It's more like looking for the fourth root of minus 16. Then you can also simplify these expressions using, De Moivre's theorem. Okay. And then the last set of practice, you have a lot to lay your hands on here. So given Z equals 3 plus 4 in rectangular form, express Z raised by 5 in polar form using the Moivre's theorem. You can do that already. Change this to polar form, use the Moivre's theorem, and then you raise the power to 5, you raise R to 5, and you multiply the angles by 5. That's all. Then find all the fourth roots of unity using the Moivre's theorem. So it's more like you have Z raised to power 4 equals 1. So it means you are looking for the fourth root of this. So, of course, the other time we had to do cos pi plus I sin pi, right? So, and cos pi is minus 1. So here we need just 1. So I think I suppose this should be 0, right? Like cos 0 plus sine 0 or something like that. I think that is what is going to work here. So you may want to try that out and see. So find all the fourth roots of unity using the Moivre's theorem. So that's what is going to happen there. Then use the Moivre's theorem to express cos 4 theta and sine 4 theta in terms of cos theta and sine theta. I did something like that for cos 3 theta and sine 3 theta. Then solve the equation Z3 equals minus 8i. So it is like you looking for the cube root of minus 8i. So no longer so maybe 180 degrees may not work here now. So because the focus is now sine, what is going to give you minus 1? That's the focus right now. So you want to think about that, So thank you so much for listening. If you have not subscribed to this channel, please do that and hit on the notification bell so you can always get alerted anytime a new video is released. See you in the next video, and thank you for listening.